In this lesson, we're going to learn how to visually display quantitative data, data that deals with values or amounts. One way to display quantitative data is through what's called a dot plot. A dot plot has an x-axis that's representing a number line, numeric values. The y-axis represents frequency or relative frequency. How you create a dot plot is for each observation in your data set, you simply place a dot at that numeric value. If multiple dots have the same numeric value, you stack them on top of each other. Here's an example of 5 observations and their coinciding dot plot. Another way to visually display quantitative data is through what's called a histogram. A histogram is similar to a dot plot in that the x-axis is a number line and the y-axis represents frequency or relative frequency. However, in histograms, observations are placed in bins. Let's see what I mean by that. To the right is a histogram of college students' height. So let's say that one student identified as having a height of 61 inches. They would be placed in the bin of 60 inches to 62.5 inches. So anybody who identified in that range would be in that bin. We can see in this example, it looks like roughly 10% of people that were sampled are between 60 to 62.5 inches. This brings up the concept of bin width. A bin width represents the length of a bin. So in this case, this bin goes from 60 to 62.5 inches. Therefore, the bin width is 2.5 inches. And we can see that the bin width for each bin stays constant, as in the next bin goes from 62.5 to 65 inches, and so on and so forth. You may be wondering, well, what happens if an observation falls exactly between two bins? For instance, if a student identified as being exactly 62.5 inches tall. Well, the majority of times how histograms work is the lower limit of each bin is inclusive and the upper limit of each bin is exclusive. So for instance, the red bin, 60 to 62.5, it includes the number 60 but does not include 62.5. So that bin incorporates everybody from 60 inches tall up to 62.4999999, repeating forever, inches tall. The bin to the right includes 62.5 and goes all the way up to 64.999999, repeating forever, inches tall, but does not include 65. So when visualizing quantitative data, one's goal should learn about the data set's distribution. When dealing with quantitative data, there's going to be 4 aspects of its distribution that we're interested in. The shape of your data set, the center of your data set, the spread of your data set, and if there's any outliers. Learning about these 4 aspects will help you make inferences about the population in which you're interested in if you're looking at a sample of data. So let's dig a little bit deeper into the 4 characteristics of a quantitative distribution. So when looking at your distribution shape, you should be interested in, is there any skewness in our data set? Is it symmetric? How many peaks do we have? Because depending on the shape of your data affects how you analyze it. We're also interested in the center of your distribution. There are different ways to define the center, such as the middle or the average, but both of these metrics will have positives and negatives. We'll learn more about how to calculate the center of your distribution in a later lecture. Another characteristic of a quantitative distribution is the spread. How disperse are observations from one another? Are they all very far out from one another? Are they very close, clustered together? Are they equally far apart from one another? Depending on how spread out your data set is, also affects how you should analyze your data. The last aspect of a quantitative distribution are outliers. Are there any observations or a singular observation that is very far away from the majority of your data? This too can affect how you analyze your data set. However, in this lecture, we're going to solely focus on shape. So when thinking about the shape of your distribution, however, in this lecture, we're going to focus on shape. So when thinking about the shape of a histogram taken from a sample of data, one's goal should try to visualize, well, what would the population distribution look like? And one way you can think about the shape of your population distribution is by imagining a smooth line through your data set. However, in this lecture, we're going to focus solely on shape. When looking at a histogram shape, however, in this lecture, we're going to focus on shape. When looking at the shape of a histogram taken from a sample of data, one should try to get a sense of, well, okay, what's going on with my population distribution, and what shape would that histogram follow? One way you can visualize the shape of a population histogram is by imagining a smooth line outlining the histogram's general shape. And the reason why that works is because the concept below, where generally speaking, the more observations you have in your data set, the more possible bins you can create, and the smaller bin widths you will have. So what ends up happening is when you take a sample of data, you don't have the observations for every single element of your population. But if you were to take every single element of your population, you would have more observations, you would have more bins, and they would have smaller bin widths. So let's look at an example representing this. Here we have two histograms representing student ACT scores. The ACT, for those of you that don't know, is a standardized test with results ranging from 1 to 36, and you can only receive whole number possibilities. You can't score something like a 25.5, you can only get a 25, for instance. The histogram to the left has less observations comprised in it than the histogram to the right. We can see the histogram to the right has more bins and a smaller bin width. The bin width for the histogram to the right is 2.5 points, and the bin width to the histogram to the left is 5 points. Now let's fit a smooth line through our histograms. We can see as you have more observations, resulting in more bins and smaller bin widths, that smooth line will represent your histogram more effectively. This is why we can envision a smooth line representing our population distribution shape, because as we take more and more observations, the shape of your histogram will look more and more smooth. Let's now classify different shapes that quantitative data can take on. The first is what's known as a bell shape. And in this shape, your data is symmetric and it has one peak. It looks like a general mound type shape. Not all sets of data follow a symmetric distribution. Here we have a shape that's known as right-skewed data, where your data tends to veer off or tail off to the right. This is actually a histogram of Instagram followers for collegiate students. Many times you end up with skewed data if one of your bounds is limited. Like in this case, you can't have an Instagram account with negative followers, so you have a bound at 0. However, your upper bound can go up into the thousands, even millions, and billions technically. So many times what happens is when you have a bound on one of your sides, you'll end up with skewed data, such as this example with Instagram followers. The direction of this skew is in relation to where's the data veering off or tailing off. Conversely, we also have something called left skewed data, where in this case your data tends to veer off or tail off to the left. You can also talk about the severity of skewness, where in some instances you can have severely skewed data or you can have slightly skewed data, depending on how strong the tail off is. Not all data only has one peak, however. You can look at data that has 2 peaks, and we call this bimodal. You also could have trimodal data with 3 peaks, or quadmodal data with 4 peaks, etc. You could also have a data set that's bimodal, has 2 peaks, and skewed to the right. So you can combine skewness and the number of peaks to classify the shape that your data takes on. Lastly, maybe your data set has no peaks. We call that uniform, which represents a horizontal line, where each observation essentially is equally likely to occur. While it may seem somewhat simplistic, describing the shape of your data is very important because it affects how you should analyze your data. Your data doesn't always take on these nice and neat, perfect types of shapes. Sometimes it can get messy. So it's very important when you first look at your histogram to get a general sense of, okay, what does the shape of our data set look like?